Hello, AP students. Today's lesson begins with Chapter 8. We'll be talking about chemical bonding. And to understand the behavior of matter around us, we have to understand the nature of chemical bonding and the factors that control the structures of the compounds as they form. Okay, so today's lesson we're going to focus on section 8.1 and 8.2, where we'll be talking about the different types of bondings, okay, and the factors that are involved in each of those bondings, and the electronegativity trend. So there'll be another trend added into our periodic table trend lesson. Okay, so these are the questions that you should keep in the back of your mind, kind of like the objectives of the first part of this lesson. So make sure you know what a chemical bond is. Make sure you can explain the aspect of why atoms want to bond to form compounds, and then how exactly do they bond? How exactly do they bond with each other to form compounds? Okay, so we're going to be looking at various classes of compounds and trying to illustrate the different types. Okay, and then we'll develop a model to describe the structure and the bonding that characterizes the different kinds of materials that you can find in nature. Okay, so what is a chemical bond? Basically, it's a force that holds atoms together and helps them to function as a unit, like a compound or like a polyatomic ion. Okay, and now when will a bond form? Well, the bond is going to form when the energy of the compound or aggregate, as they're using here, is lower than the actual energy of the separate atoms themselves. Okay, so that's basically the bottom line, because in nature, we always want to go towards stability, which is the lowest possible energy state. Okay, so here's an example of two hydrogen atoms. Okay, and so when we bring the two atoms together, as you see starting to happen down here, okay, there's a couple of things going on. We got some potential energy and kinetic energy changes happening. Okay, we've got positive ion repulsions. We got proton repulsions, and then we've got our electron repulsions, and then we have the proton-electron attractions. So there's a lot going on there. Okay, so when the hydrogen atoms come close together, what's happening is the repulsions are being minimized, the attractions are being maximized, and what ends up happening is the hydrogen molecule then ends up in a lower energy state than the actual separated ions. Okay, so this bond length here is the minimal distance or the minimal energy needed between those two molecules. Okay, so we can see that in this slide they're showing here. Notice that it's becoming more negative, meaning energy is being released, more stability, and that point is at this distance. Okay, and then there we go. Hopefully that took care of that. So now we see an increase again until we hit 0 when they're completely separated. So this is just giving you the visual of that concept. Okay, so let's go into the specific kinds of bondings. Now, in the last slide we were talking about hydrogen there. That was an example of a covalent bond where electrons are being shared equally. Then we also have what's called an ionic bond. And ionic bonds take place when electrons are completely transferred. Now, if you recall, metals have low ionization energies. It doesn't take much to remove those electrons because they don't really want to have them. The goal is stability and full energy shells. So electrons have low ionization energies. Metals have low ionization energies, and nonmetals have high ionization energies. So they really have an affinity for that electron. And so when metals and nonmetals are put in close proximity, are put in close proximity to each other, that electron will be completely transferred. An electrostatic bond will take place, and that molecule or that ionic compound now will be in a lower energy state. And the idea behind that is an important concept dealing with Coulomb's law. And so I'm going to just insert a slide here to talk a little bit about Coulomb's law, because Coulomb's law is used in several topics throughout the year. And so we want to make sure that we take some time to look at that. Coulomb's law is an important concept to remember because it's used in several topics throughout this year's chemistry course. And the idea behind it is that you can get the energy of interaction between two atoms, whether like charges or different charges, okay? You can get that energy of interaction between them, okay? So for example, let's look at the formula, okay? The energy of interaction between the two ions is taking this constant here, multiplying it by the charges of the two ions, and dividing it by the difference between the atom nuclei. Okay, the distance is in nanometers, and energy is in joules, thus the units for this constant. Okay, now it's not so important to remember this constant as it is to remember that the greater the charge, the greater the energy. Okay, the greater the distance, the lower the energy. See that inverse relationship between distance and the direct relationship between charge. That's the important concept to remember. But let's look at this with the sodium chloride compound. Okay, so we've got a positive ion and a negative ion. So if we plug them into our formula here, okay, and then we get our charges. Sodium is a +1, and chlorine is a -1. Okay, and then the radial difference between those two nuclei is this many nanometers, so 0.276 nanometers. Okay, we punch that into our calculator, and we get a negative value. And that negative value means lower energy state than sodium or chlorine, and energy is being released because they're attracting. Okay, and so we get the negative value. Okay, and energy is in joules. Now, if you put two like charges together, you're going to get a positive value, and that's an indication of repulsion, not attraction. So that's the idea behind Coulomb's law. And remember, the important thing is the direct relationship to charge and the inverse relationship to the distance. Okay, so what about in our covalent bonding situations, what happens when they don't share equally, when we get these intermediate cases? Okay, what's going on there? Well, what happens is one atom has a stronger affinity for that electron than another atom, but not enough to completely transfer the electron. So what happens is we end up with this charge separation, okay, a partial positive, and we denote this with a delta symbol, if I can draw that very well. Okay, this is supposed to be the delta, the lowercase delta. Oops. Okay, ignore that little blurb there. Okay, and what happens is we've got charged ends. Okay, and so that tends to lead us to then that unequal sharing. And so in the next slide, we see evidence of this taking place when hydrogen fluoride is put into the gaseous state, so the molecules are completely separated, and then an electric field is placed on them. We see them lining up end to end. And if you remember back in CP chemistry, we showed water molecules having polar ends by using a balloon and a stream of water, and we were able to deflect that stream of water. Okay, this is just evidence that we get fractional charges or positive and negative ends. So in the next slide is a video clip explaining this experiment.
A polar substance, as indicated by the positive and negative signs on the molecules, is placed between metal plates. When the plates are connected to an electric voltage, the polar molecules align positive to negative.
Okay, so that was just giving us that idea of the separated charges. Now, if this is hydrogen fluoride, many times you'll see it the bond presented like this, and they'll draw those delta symbols below it. So showing that the hydrogen end is the positive or positive polar end, and the fluorine is the negative end. Okay, so let's do a concept check now, if we possibly can get off of this slide. All right, so can you answer now what is meant by the term chemical bond? Okay, a force that holds atoms together as a functioning unit. And why do atoms bond with each other to form molecules? To become more stable, to have a lower energy state than the individual atoms themselves. And then how do the atoms bond with each other to form the molecules? Well, they either share those electrons, either equally or unequally, or they transfer them between the atoms. Okay, so now let's move on to the idea of electronegativity, and this is now another trend in the periodic table. So remember we had talked about ionization energy, electron affinity, atom size, metallic character, and now we're looking at electronegativity. And because all the atoms have different attractions for the electron, okay, we see a trend that plays out, and we define this term as the ability of an atom in the molecule, okay, so when they're bonding, it's the ability of the atom to attract the shared electrons to itself, okay, and so the values are used for this generic HX here, generic element, and they're determined by comparing the measured bond with the expected bond. That's how they come up with these values, okay, and the values are in a pattern on the table that goes increasing across, okay, and then remember we always want to be thinking about increasing. So across the period, the desire for the electron increases during that bond, and then in a group it increases this way, okay, and so the desire for the electron increases as we go from bottom to top. Okay, and we'll talk about why that is as we walk through the lesson. Okay, and so notice our scale. Fluorine highest with 4.0, cesium lowest down here on the table versus up here on the table. Fluorine, cesium lowest with a 0.7. Okay, and so that's the values we use for the electronegativity character. Okay. So on this slide, it's just trying to give you the visual for the electronegativity values and their increasing patterns. And so let's peek again over here at fluorine, so we kind of really stick that number in our mind. And then notice around it, oxygen greater than chlorine, chlorine greater than sulfur. Okay, and then as we come over here, again, try to think of the pattern as going up, increasing, instead of trying to remember increasing and decreasing. Can't draw too well, huh? So lowest value down here. Okay, so here's a little quick check. If fluorine and lithium react, okay, which has more attraction for an electron? Okay, now we know that because they're in the same period, right? Lithium over here, fluorine over here, okay? So why the greater attraction? That's the important question. We can see the pattern. Well, you can't just say because the arrow goes to the right, because it increases to the right. You can't use that as a justification. You have to talk about why that happens. Okay? And so think about what's going on in the same period here. Okay? As we go across the periodic table, we're gaining more and more protons. Well, we're also gaining electrons, but we're in the same energy level. So the electrons are staying the same distance. So fluorine, having more protons, greater effective nuclear charge, has a stronger desire, can pull on those electrons more. So it's going to have the greater attraction. Okay, so that's what happens in a period. Now, what about fluorine and iodine? Now we're attempting to look at a group. Remember, increase is going up. So again, fluorine is going to have the greater attraction. How come? Kind of the same idea, except with a little twist. Yes, iodine has more protons, but its electrons are becoming further and further from the nucleus due to gaining of energy levels. And so you've got a lot of shielding going on. Okay, so that's a key word, shielding. Okay, so fluorine, having that electrons closer to the nucleus, it's going to have a stronger desire. Iodine, having that shielding going on. Okay, so what's the general trend? Make sure you can state that general trend and explain why. Okay, so it's up and over. Okay, and why? Well, you want to be talking about protons increasing here. So a stronger effective nuclear charge. Okay, so therefore greater desire for those outer electrons. Okay, down here it's low, not a strong desire because we've got shielding. So yes, there are more protons, but the effective nuclear charge, the strong pull, that's what that means, effective nuclear charge, the protons that are having any effect on the outer electrons, it's minimized because of this shielding. Okay, less shielding up here, so of course a greater affinity, a stronger desire for that electron during a bond. Now this table lays the electronegativity difference and the bond timeout type. It lays it out very well. We know covalent bonding takes place between nonmetals. Okay, that's your molecular compounds. They have very little electronegativity difference because they're sharing so well. They both have equal desires for the electron. But then as we start to head toward the ionic compounds, the metal nonmetals, now we have a greater electronegativity difference because of a different desire for that electron. Okay, now there is in general scale you can use to break them into types, but there's gray areas in that scale. We can talk about that scale in this next slide. So before we lay out the scale, let's just see if you can put each one into their bonds from most polar to least polar, meaning the greatest electronegativity difference to the least electronegativity difference. Okay, now what are you going to be thinking about? You're going to be thinking about their positions on the periodic table. Okay, the further they are from each other, the greater the electronegativity difference they're going to have. Because remember, the trend goes up and over. So the more distance you have between them, the greater the trend will be. And then the scale we tended to use was if the difference was 0.4 or below, okay, we were covalent. We were sharing equally. We were nonpolar. Okay, then if we hit 0.5 to about 1.9, and again there's gray areas in this, then we've got our nonpolar. We're starting to not share equally. And then when you hit the difference of 2.0 or up, then you tend to be ionic. Okay, but again, gray areas, so if you can, try and use the periodic table instead of the scale. Okay, so let's see if you've chosen correctly. Okay, and hopefully that went well. All right, here's a couple more concept checks. Which of the following bonds would be the least polar, yet still be considered polar covalent? Well, remember that you still have to have unequal sharing, so you're not going to pick something like this, okay? And then you know that there's sharing going on, so you're not going to pick a metal, non-metal. So you're going to try and think about the idea that there's still unequal sharing, but you have to choose the bond with the least difference. So closest together, but yet unequal, if that makes any sense. And so hopefully you picked NO. All right, let's try the next opposite. Which of the following bonds would be the most polar without being considered ionic? So again, we throw this one out because we know that's ionic. Throw this one out because we know they're equally sharing. Now we got to find one that's got the greatest distance, but yet not be completely removed, and not be ionic. Okay? And so hopefully you picked silicon oxygen. Okay, so that ends our lesson on the types of bonds we have and electronegativity. And then in the next lesson, you can see we're going to talk about bond polarity and the idea of dipole moments.